Here we'll examine three different geometric measures of volume, arc length, and surface area, and how we can use calculus to be able to compute each of these quantities. We'll first start by examining volume. When we think about volume from a geometric perspective, we oftentimes can think about volume as being the product of capital B and H, where we think of capital B as being the area of a base, and then H as being the height of the solid. So in the specific example of the three-dimensional solid of the cone that you're seeing right here, this quantity right here, the area of the bottom of that shape, would be considered the area of the base. And then we would just multiply it with the height. Okay, and the important thing that you want to really recognize here is that there are a bunch of bases that are like similar in shape to that circle that really could just like slide along the height. And if we just like slid a bunch of circles um, along that height, it would fill up the volume of this cone. And so it's that kind of general idea of how we figure out volume geometrically that we can also do using calculus. Okay, so calculus gives the name slice method to this way of being able to compute volumes. So the way this works visually is if you have a cross section of a solid that you can actually move all the way through the solid, then you can actually use calculus to be able to figure out the volume of this. So in the context of this pyramid, that cross section right there is a square. And so you could really just like add up a bunch of like tiny square volumes that fill up the entire pyramid and you get the volume of this solid. Okay. So in general, if you can figure out some sort of a function that equals the area of that cross section that you can slide all the way through the three-dimensional solid, then you can figure out the volume of the solid by integrating that area function that would be the cross section with respect to that same variable x. And then you would just need to integrate from these two values, a and b, the lower and upper heights along that axis on which you would slide that cross section. We'll employ the use of the slice method to be able to find the volume of a solid here. We're given that the base of a solid S is a circle of radius 4 that lies in the xy plane. The cross sections of the solid that are perpendicular to the base are isosceles triangles that each have a height that is 1/5 as long as the base, and we want to find the volume of this solid S. So we are given that in the xy plane, there is a base of the solid that is a circle of radius 4. So we could just center that circle at the origin. And then because it is of radius 4, we could say that this is 4, -4, and -4, and 4. And then the cross sections of the solid that are perpendicular to the base. So at a 90-degree angle to that circle then, so like projecting upwards as sort of like a height, are all isosceles triangles. And they go perpendicular to the base. So you could basically have, like right here, for example, the base of the isosceles triangle. And then if you imagine, right here you have an isosceles triangle cross section. And so if those isosceles triangles just like slide all the way through the circle, right? So like right here you'd have a longer base for an isosceles triangle, so a little bit of a taller height, right? Basically, you'd get kind of like a rounded top sort of shape that then we want to find the volume for, right? So because of the fact that you have that isosceles triangle cross section that moves all the way from -4 on x to 4 on x, then you can just integrate from -4 to 4 then whatever the area of that isosceles triangle cross section is with respect to x, and that's going to give you then the volume of what this solid is here. Now, because of the fact that this solid is symmetrical over the y-axis, I could actually just integrate from 0 to 4 and then just double my answer because it'd be the same value from -4 to 0. So just for simplicity's sake then, I will take advantage of that. So we'll just go from 0 to 4 then and just double that integral to get the full volume there. So then we just have to be able to figure out some function for the area of that isosceles triangle therefore then. So the isosceles triangle cross-section would have an area that would be half times its base times its height from area formula for a triangle, right? Now, the base of the triangle kind of fluctuates because you might have a longer cross-section for the base. So what we always know to be true, though, is that halfway across the base of that isosceles triangle is actually just like a distance that's touching the circle, and it's always dependent on the circle. So we'd have to know about some sort of a function that defines a circle, which we know a lot about. Because for a circle that's centered at the origin, you can just have x squared plus y squared equal the radius squared. Now the radius is 4, and 4 squared is 16. So x squared plus y squared equals 16 defines that circle. And then specifically, this distance right there in the teal is really just like the y value on this portion of the circle right here. And that portion of the circle would be the graph of y equals the square root of 16 minus x squared, if we just solve that equation for that, right? So since that's the y value, then that's going to be square root of 16 minus x squared long. And then to get the full base, you just need to double that, since that's also square root of 16 minus x squared long. So we know that this base of the isosceles triangle cross-section is going to be 2 square root of 16 minus x squared long. And then the height of each isosceles triangle cross-section is 1/5 as long as its base. So it's going to be 1/5 times 2 square roots. It's 1/5 of the length of the base. And then you have the half right there, which of course is going to stay half. So if you just multiply that with that, with that, with that, that would be all the numbers. Half times 2 is 1, and then 1/5 times 2 is 2/5. Times 2/5 is 2/5. And then square root times square root with the same radicands just makes it become normal. 16 minus x squared, which will multiply by 2/5, which then yields 32/5 minus 2/5 x squared. So with that then, that gives you the area of the isosceles triangle cross-section. So we can take this right here and say that it is equivalent to 2 integral from 0 to 4 of 32/5 minus 2/5 x squared dx. All right, great. I'm going to multiply the 2n. So let's change this to be 64/5 and 4/5 then. Then we can find antiderivative of 64/5 and negative 4/5 x squared. So antiderivative of 64/5 would be 64/5 x. And then you can increase the exponent there to 3. And then multiply by 1/3 with the 4/5. 1 times 4 is 4. 3 times 5 is 15. So you get a coefficient of 4/15 in front right there. Then you can evaluate from 0 to 4. And when you plug in 0, you're going to get 0. Yeah, so it really just becomes right there, 64 times 4 is 256 over 5. And then 4 to the third is 64, and 64 times 4 is 256 again, but that's over 15. So then you need to get a common denominator, which means you can multiply this one by 3 over 3, and you get a common denominator of 15 then. Ends up being 768 over 15 minus 256 over 15, which then ends up being 512 over 15. Okay, and then we're finally done. So that would be the volume, and that would be in cubic units for that three-dimensional solid there. In addition to the slice method, the disk method and washer method are methods for finding volumes of three-dimensional solids. For both the disk method and washer method, these are methods for finding volumes of solids that we call solids of revolution. So That means that you're revolving an area of a region around some axis, and then it creates a three-dimensional solid. So looking at the disk method, first of all, what you're going to do is you're going to take some sort of an area of a region, and then identify an axis of rotation that you're going to spin that region around 360 degrees. When you do so, it creates this three-dimensional solid in this particular case right here. And what you'll notice is that each of the cross sections, so if you like slice into this parallel to the direction which you rotated right here, each of those cross sections are circles, which are also known as disks. Okay. So then to actually find the volume of that whole thing right there, we actually really do use the slice method because all of the cross sections are just circles, are disks. So you could just slide all of the circles along that axis from A to B right there. So the volume is just going to be the integral from A to B and of the area of the cross sections. Now the cross sections are circles, so it'd just be pi r squared because that's the area of a circle. And then we do so with respect to x because that is the axis that A and B are on, right? So, like, you'll have to figure out then something for r that is in terms of x. You'll notice that the radius of the circle could be thought of as just the y value to the curve f of x right there, since it's just the distance from the x-axis to the curve. And you'll see that it's important to recognize that it's f of x, right? Because that radius does fluctuate all the way, all the time. So, you'll have to substitute in that case, like f of x for r. But in general, this is generally all you'll see a formula for disk method. We'll look at examples in a little while. And then the other method is called the washer method. And there again, it is a method for finding volume for solids of revolution. You'll again take an area of a region, like I've colored in red right there, and you'll revolve it around an axis of revolution. But what makes the washer method different is that you're going to spin it around an axis of rotation where there's at least a little bit of a gap between where the area of that region is and then the axis of revolution. What that causes to happen, there's a little bit of a gap then, is then the cross sections of the solid will have some empty space at some point inside of there. So those cross sections are all washers. So this is why we call it the washer method. Okay. So formulaically, the math that we're going to need to do to be able to figure out the volume of a solid that has washer cross sections is if you actually had this whole area right here that you revolved around that axis of rotation, you could use the disk method and just do pi r squared if you treated like this distance right here as r, right? But then that would give you the full filled in entire volume of this whole solid without any empty space. So if you want to create any empty space, then you've got to subtract away some inner volume. So that means that if you took this area right here, where that empty space, where that gap is, and then revolved it, you could find that by doing pi, and then you have a little different radius right there. So you could call this like little r for a smaller radius, little r squared. And then subtract away that integral, and that's what you have right there. So it's really just like finding the full volume minus the inner volume, like the inside of it, and subtracting away, and that's ultimately how the washer method's going to work. You're asked to find the volume of a solid that results from rotating a region between the graphs of the given equations about the indicated line over the indicated interval. So we'll be looking to find basically the volume of some solid of revolution. So we'll definitely need to investigate whether it has a disk cross-section or a washer cross-section as we think about what's happening right here. So you'll see that right here, this will be kind of like the bounds on the region, the area that we're going to revolve. We'll also need to know about this. This will actually kind of help enclose the region entirely, in which we're going to revolve around that interval, of course. The last thing that's given here is going to be actually our axis of rotation that we're going to spin the area around. So if we just sketch out what is happening in this scenario, we've got the graph of y equals cube root of x plus 1, which should be the cube root function shifted up 1 unit, so it should look something like this. And then we also have y equals 0, which would be a horizontal line, actually is the x-axis. And then on the interval from -1 to 4, so actually right there at an x-coordinate of -1 is the x-intercept of that cube root function, and then you go all the way to 4 over here. So the area that is enclosed there would really be like this blue shaded area right here between the graphs on -1 to 4. And then we want to revolve it around the horizontal line y equals 0. So therefore, this is going to be our axis of rotation. So the thing that you'll notice then is that where that region is in location relative to the axis of rotation is right against the axis of rotation. So therefore, when we rotate this all the way around 360 degrees, we're going to have disk cross sections or circular cross sections. So all that we would need to do then is just integrate pi and then whatever the radius of those disks is squared. So since we're revolving around a horizontal axis, we're going to integrate along the x-axis then, which then means we can set up an integral that's with respect to x, and then we can use -1 and 4 as your integration limits there. We'll want to be able to figure out what that radius actually is. So your radius is really what this distance is right there, which is really the distance between the cube root function and the x-axis. So it'd really just simply be the y value of the cube root function, which is cube root of x plus 1 in terms of x. So we'll have an integral then that will look like square the cube root of x plus 1, and then go from there. So because the quantity is squared, we could FOIL that out and make it a little bit easier to find an antiderivative then. So just off to the side right here, if I put cube root of x in exponential form, it would be x to the 1/3 plus 1, and then times another x to the 1/3 plus 1. We'll want to FOIL up. When we do x to the 1/3 times x to the 1/3, we get x to the 2/3. And then x to the 1/3 times 1 is plus x to the 1/3, and we get another one of them, so plus 2x to the 1/3, and then finally 1 times 1 is plus 1. So then we can just replace that binomial squared with this perfect square trinomial. And then I'm going to throw that pi outside right there. We can always pull that constant in front. Okay, so then we can just find an antiderivative of the integrand here, and then plug in 4, -1, subtract, and we're good to go. So this fella right here, we can just raise the exponent by 1, which would make it become an exponent of 5/3. So then multiply by the reciprocal of 3/5. This one right here has an exponent of 1/3, so we can increase it by 1 to become 4/3, and then multiply by the reciprocal of 3/4 in front with that too. And then the antiderivative of 1 is x. And then we can evaluate that between -1 and 4, and then multiply by pi. This one becomes a little bit messy that when you plug in the 4 and then you plug in the -1 and subtract. I'm just going to kind of skip over that work and just tell you that you get about like 19.67 something, and then you have to multiply that by pi. And then once you multiply that by pi, you end up getting like 61.81 as an approximate solution there for the volume. So therefore, that volume there is going to be 61.801 cubic units approximately. And then for this problem right here, we have another solid of revolution that we want to find the volume for. A little bit of different bounds right here. So we have, this is still the same though. So you've got the cube root of x plus 1. And then you also have the vertical axis x equals 1. Or a vertical bound, I should say. And then you have a horizontal bound. It's the constant function of y equals 3, like this. And so that's going to form our region. So it's going to be this region right here that we are going to revolve. And then this right here is going to be that axis of revolution that we're going to revolve around. So we're going to revolve around x equals 1, which would actually be this right here, x equals 1. So you can see that that region completely borders the axis of revolution. So when you revolve it, we will get just circular cross sections then, or disk cross sections. Now, because we're going around a vertical axis here, when we set up this integral of pi r squared for the disk method, we're going to have to integrate with respect to y then. So it'll be really convenient for us then to be able to figure out what this y value is, as well as this y value that our region fits between. The higher one is a little bit easier to tell. It's 3 because it's right at the constant function. The lower integration value we would have to solve for, I guess, because it's right at the intersection of the vertical line x equals 1 and then the cube root function of y equals cube root of x plus 1. So we could figure out where those intersect. I guess we could plug the x equals 1 in right here, and then cube root of 1 is 1, plus 1 is 2. So when y equals 2, that's what we want right there, is when y equals, there we go, when y equals 2. So that would be the lower limit. So the only thing that we really need here then is we need what the actual radius is in terms of y. So based on the region right here, this distance right here is going to be the radius that we're going to revolve around 360 degrees around that x equals 1 axis of rotation right there. So that radius is a little bit longer than this teal distance right here. So this teal distance would technically be the x value of y equals cube root of x plus 1, since it's the x value going to that red graph right there. But this yellow part right here is not going to be on it, and that's 1 long. So we'll just need to subtract away 1 from that x value. So you're going to have to take that equation of y equals cube root of x plus 1 and solve it so that you get x alone in terms of y. So if you subtract 1 first from both sides, you get y minus 1 is equal to the cube root of x. And then you can cube both sides, and y minus 1 all cubed is going to equal x then. Yeah, so that would be that whole teal distance that I had, but we want to subtract away that 1 so that we only get just the radius right there. So your radius is going to be y minus 1 all cubed, and then subtract 1. So that's what we want to substitute in for the radius here then. So when we do so, we're going to get an integral that looks like this, integral from 2 to 3. I can pull the pi in front. And then we want the square of the quantity of y minus 1 cubed minus 1. Yeah, all squared dy. So this is kind of similar to the one just before, where we really have kind of 2 individual terms right there. So like the square of a binomial. If we FOIL that out, y minus 1 cubed will multiply with y minus 1 cubed. So you have y minus 1 to the 6th, and then y minus 1 cubed times 1 is just y minus 1 cubed, but you're going to have 2 of them in the FOILing. So minus 2 y minus 1 cubed, and then negative 1 times negative 1 is positive 1. So that just gives us an equivalent expression to be able to integrate based on squaring that binomial. And then we can try to integrate each of these like separate terms. So technically you have like a y minus 1 that's plugged into 6. So like you'd want to let your u equal y minus 1, which then means your du is equal to 1, so just dy. So nothing fancy is really going to happen. So like if you put in your u and then now you're anti-differentiating u to the 6th, you just increase the exponent to a 7, multiply by 1/7, then you have your u inside of that. But when you put your u back in of y minus 1, then it's just that. So nothing crazy happens. So for similar reasoning right here, this is going to be raised to the 4th. And so then you'll put that over 4, which that simplifies to 1/2. So you get that, and the antiderivative for 1 is just 1. And so then that you can evaluate between 2 and 3, and multiply all of that by pi. I think I'll work through all of this right here. It doesn't turn out incredibly as crazy as the last one, I guess. Okay, so we'd want to plug in 3 first of all. So you'd have 1/7. If you plug in 3, you'd minus the 1 and become 2 to the 7th then, and then minus half. Again, you get a 2 when you put in 3, and then plus 3. That whole thing right there. And then you subtract this whole thing of where if you plug in 2, you get 1/7. 2 minus 1 is 1 to the 7th, minus half, 1 to the 4th, plus 2. And then all that gets multiplied by pi. This becomes 2 to the 7th is 128, so it's 128 sevenths. And then 2 to the 4th is 16, and half of that is 8. Plus 3. Minus, and then you get like 1/7 minus 1/2 plus 2 going on right there, and all that gets multiplied by pi. Okay, and then you work through all of that and you do all the fraction work with that, right? You're going to end up with a solution of 163 over 14 pi then, and that would be in cubic units. Here we're asked to find the volume of another solid of revolution. We've got the cube root function shifted up 1 unit as one of the bounds on the region here, as well as the linear function y equals 2x. And then the constant function y equals 3. So we're looking at this region right here, and we're about to revolve this around this axis of rotation, x equals 0, which would be this vertical line right here. So we're going to spin it around like this. So you'll notice then there's actually a gap between the area that we're revolving an axis of rotation. So right here, this would be the little r, the little radius, whose volume, when we revolve, we want to subtract away from the volume we get when we find the overall volume of this right here revolved. We'll call that big R, which is really just the distance between the axis of rotation and then the curve y equals cube root of x plus 1. So really, this is the x value of the curve. It's just x, right? It's just a little horizontal distance. And then this little r is also the x value, but it's the x value on the blue curve. So for the blue curve, since you have y equals 2x, then x would equal 1/2 y. So we could use 1/2 y for the little r then. And then since y is equal to the cube root of x plus 1, when you solve that for x, x is equal to y minus 1 quantity cubed. So you can use that for big R then. So then we'll have to use the washer method, which is integrating pi big R squared and then subtracting pi little r squared. So specifically, since we are doing this washer method here, and we're revolving around a vertical axis, then both of these integrals are going to be with respect to y, because of that revolving around the vertical axis. And then we'd want to find integration limits here too. It's revolving between here and here, which is 2 and 3. If you plug in the big R was going to be the y minus 1 quantity cubed. And then the little r was 1/2 y. So if we simplify these integrands, y minus 1 all cubed and then squared, you'd multiply these exponents right here, so it becomes y minus 1 to the 6th. We'll want to find an antiderivative for just a little bit. And then we could simplify the 1/2 y squared to become 1/4 y squared. And then we can find some antiderivatives for these now. So as we talked about in a previous example, when we let u equal y minus 1, and then we would know du is just going to be dy, then we can just know that when we raise it to the 7th and then multiply it by 1/7, that's all that's going to happen. Then use substitution. You can put the y minus 1 back in, and then evaluate between 2 and 3. And then here you're going to increase the exponent to a 3, and then multiply by 1/3 in front, along with 1/4 in front. So 1/4 times 1/3 is 1/12. All right, and then we can plug in 3. 3 minus 1 is 2 to the 7th times 1/7, and then minus, plug in 2, it's going to be 1 to the 7th. And then 3 cubed is 27, so 27 twelfths, and then 2 cubed is 8, so 8 twelfths. 2 to the 7th is 128. So 128 sevenths minus 1/7 is actually 127 over 7. So I'm just going to write it like that. Pi. And then 27 twelfths minus 8 twelfths, they both have a common denominator of 12. So you just subtract 27 and 8, which would be 19. So 19 pi over 12. And then you also get a common denominator there. So multiply this one by 7 over 7. This one by 12 over 12. You get a common denominator 84 then, since that's 12 times 7. 1524 over 84 pi minus 133 over 84 pi. Let me subtract. You get 1,391 pi over 84. Maybe it reduces, maybe it doesn't. Anyways, we got an exact enough answer of that there. Here in this example, we have the same region as before. It's just we're going to revolve it around a little bit of a different axis of rotation here. It's going around x equals -1, so it's still going to be a vertical axis. So we could integrate with respect to y then. It's just we're going to have a little different outer and inner radius. So you can definitely see, of course, right, that we're going to have to use the washer method because of the fact that there's a gap. So now this inner radius right here is longer by 1. So originally we said that this part of the inner radius was 1/2 y long, but now with this additional unit between, then 1 plus half y is going to be what that inner radius is going to be. And then the outer radius from here to there will be an additional 1 added to that quantity of y minus 1 cubed that we had. So our integral will still go from 2 to 3 like before, but then we're going to have to do pi, and then our big radius that we're going to have to square is going to have to be the quantity of y minus 1 cubed plus 1, and then subtract pi integral from 2 to 3 of the square of our inner radius. I'm just going to be adding 1 to the 1/2 y. Once you then have these integrals set up and you FOIL out, you're going to have y minus 1 to the 6 plus 2y minus 1 to the third plus 1 that you'll have to anti-differentiate and then continue evaluating from there. And then here, your expanded integrand would be 1/4 y squared plus y plus 1. You'll anti-differentiate. Okay, you do all the math of that. If you want to go through that on your own, go ahead. This would be your answer. If you want to check your answer, it should end up being 1811 over 84 pi. Here we'll look at determining the length of various arcs. From geometry, we were able to find lengths of some easier things. So for just straight line segments, you can really just use distance formula or Pythagorean theorem to find the length of any just straight line segment. So from the Pythagorean theorem, this is the change in y and this is the change in x, that you could square both of them, add together, and then square root it, and you get this distance, right? So in other words, the distance is the square root of the sum of the square of change in x and the square of change in y. We also were able to figure out distances along circles as well, because circumference is pi times diameter. So if you had an arc, which is just a portion of the circumference, you just figure out what fraction of the circumference you need and go from there, right? But for curves like this that are not linear and that are not on a circle, it's a little bit more complicated. And so that's where calculus is going to kick in to be able to figure out the length of an arc. So what we know about arc length from calculus is that S can denote the length of this arc. And as long as you know that that arc is along some curve whose equation is y equals f of x, and you're looking to find the length between two x coordinates of a and b, then the arc length is going to be the integral from a to b then of the square root of 1 plus the derivative of that function squared. So with respect to x. So an example of finding arc length here, determine the arc length of the curve defined by the equation y equals x to the third over 3 plus 1 over the quantity of 4x over the interval from 1 to 3 along the x-axis. So, pictorially, you're just trying to figure out between 1 to 3, so somewhere up here, it's going to go off the graph, right? You're just like figuring out how long that little arc is going to be, right? So since we do have the function expressed in terms of x, and we know that it goes between 1 and 3, we can just set up our arc length integral with respect to x. So the arc length will be the integral from 1 to 3 then of the square root of 1 plus the square of the derivative of our function. We're going to have to figure that out in a little bit, dx. So let's figure out the derivative of our function, right? So here's y, so then y prime would be, if you brought the 3 down, it would multiply with the 1/3 that you really have in front right here. So 3 times 1/3 would equal 1. So then you just have 1x squared, because you decrease the exponent by 1. And then this right here, we're differentiating currently is 1/4. Since you're dividing by x, it's x to the negative 1. And then you'll have to do power rule. So bring the negative 1 down to multiply with 1/4, which will make it negative 1/4, and then decrease the exponent by 1 to become negative 2. So that is your derivative that we can plug in right here of x squared minus 1/4 x to the negative 2. So then we'll need to evaluate this integral, right? So we'll have to FOIL out this right here. So it's going to be x squared minus 1 over 4 and x squared on the bottom right there, multiply with another x squared minus 1 over 4x squared there. You do the first times the first, you get x to the 4th. And then you do the first times the last. The x squareds will cancel because you got x squared on bottom and on top right there. So it's just going to be negative 1/4. And then the same thing is going to happen right there. So you get another negative 1/4. And then finally, when you do the last times the last, you're doing a negative times a negative, which become positive. And then 1/4 times 1/4 is 1/16. And then x squareds are both on the bottom, so you're going to get x to the 4th on the bottom when you multiply. And then I should still have this plus 1 in there as well. So 1 plus all of that. Okay, so then the constants of 1 and negative 1/4 and negative 1/4 you can add together, which would become positive 1/2. So the square root of x to the 4th plus 1/2 plus 1 over 16 and x to the 4th down there. Okay, so it's a little complicated of an integral because you got funky stuff underneath that square root. So picking u as that, your du would be really complicated, but you don't have your du anywhere in the integral. So algebraically, though, things can turn out a little bit pleasantly if we factor the inside of this, because x squared times x squared would be x to the 4th. And then to multiply to equal that, you can have 1 over 4 and x squared on the bottom as well. And then when you do this part of the FOIL and this part of the FOIL right there, you get 1/4 plus 1/4, which would equal the 1/2 in the middle. So that means that, yeah, it factors nicely as x squared plus 1 over 4x squared times another one of the same thing. So then it really just factors as that binomial squared, and it's under a square root. So the fact that you have something squared under a square root means it all cancels, so then you just get the integral from 1 to 3 of just x squared plus 1/4 times x to the negative 2 dx. Okay, so now it's pretty easy to anti-differentiate. So now we're anti-differentiating, so this x squared, you're going to have to increase the exponent by 1 and then multiply it by the reciprocal. And then this one right here, you're going to have to increase the exponent by 1 and then multiply it by the reciprocal of negative 1, which is negative 1, so it just becomes minus 1/4. And then you can evaluate that between 1 and 3. So if you plug in 3 first, you have 1/3 times 27 minus 1/4. 3 to the negative 1 is 1/3. And then you can plug in 1. So it would be 1/3 of 1 minus 1/4. 1 to the negative 1 is 1. So 1/3 of 27 is 9. 1/4 times 1/3 is 1/12. And then 1/3 minus 1/4 would be like 4/12 minus 3/12. So it becomes 9 minus a 12th. And then minus another 12th, because 4/12 minus 3/12 is 1/12. If we get it all in terms of 12s, 9 is 108 12s. So it's 108 12ths minus 2 12ths, which should be 106 over 12. You can simplify and divide by 2 and get 53 over 6. And then you're golden right there. So that would be the length of the arc right here, then on 1 to 3. We'll last examine some things related to surface area. You'll recall from geometry that surface area is really being able to find the total combined area of all of the outside faces or just the outside of some sort of a geometric figure, right? So like with the picture you're seeing right here of the room, the area of all the walls added along with the ceiling and floor, like would give you the surface area, right? Which we could easily geometrically find because you could find areas of rectangles pretty easily, right? If we're going to try to find the surface area of this shape, a little bit more complicated, right? And this is where calculus really helps to kick in and be able to figure this out. So you'll notice that the solid that is actually pictured right here is specifically a solid of revolution because we're revolving some area around an axis of rotation 360 degrees. And that's the kind of surface area we're going to figure out here. So this actually is your axis of rotation in this picture. And then if you think about it, if we only take just this outer edge of the curve right here and just revolve that part around entirely, then you're gonna get really just only the outer like shell of this solid, right? Just the outer part. And that's all that we really care about, right? Is to be able to find the surface area. So what we want to be able to do then is really kind of take that distance that one cross section would have around it, so really like the perimeter of it or the circumference of a circle. We know from geometry that circumference is equal to pi times diameter, which is 2 pi r. And for calculus speak, we're going to use 2 pi r because you'll notice that actually the radius of any cross section is actually going to be f of x in this case. Okay. So we'll want to integrate that. We have to keep into account right here what the actual length of this curve is right here. And the way we could do that is by using arc length. So in a nutshell, surface area is really just going to be 2 pi, and then we'll integrate from a to b of the function and then times the arc length of the function. So 1 plus the derivative of the function, all squared, and then dx. In this example, we're asked to determine the surface area of a solid that is obtained by revolving the curve defined by the equation y equals 1/2 x minus 1 over the interval where y is between 0 and 2 about x equals 1. I actually want to change that to x equals 0 to be our axis of revolution. So that means that really we're just going to revolve around the y-axis then. And we're revolving the portion of the curve that's between 0 and 2 on the y-axis. So of course, therefore, we're looking at this region right here that we will revolve around the y-axis, get a three-dimensional solid, and we want to find the lateral surface area that we would get when we revolve that around. So because we're doing this around a vertical axis, it'd be nicest to integrate with respect to y if we can do that here, which it is really slick to be able to do so. So that means that for this function right here that is a function of x, we want to write it as a function of y instead. So y plus 1 equals 1/2, and then you can multiply by 2 to get rid of the half. So 2y plus 2 is going to equal x. So now you've got x written as a function of y. So then you would know that this distance right here is 2y plus 2, because that's equal to x. So then when we find surface area, the surface area set up as an integral is going to be 2 pi, and then we would integrate. And because we're doing this with respect to y, we would want to figure out what these coordinates are right here, which would be 0 and 2, therefore. And then multiply by f of y, and then the square root of 1 plus the derivative of f of y all squared, and then integrate with respect to y like that. So we can replace f of y right here with 2y plus 2. And then since f of y is equal to 2y plus 2, then the derivative of f is going to be just 2, because that's the derivative of 2y, and the derivative of 2 goes away. But then we'd have to square that, because we need to plug that in, so the square of that would be equal to 4. So now our integral becomes 2 pi integral from 0 to 2 of the quantity of 2y plus 2, and then square root of 1 plus 4 dy. Now the square root of 1 plus 4 is just the square root of 5. And that's just a constant multiplying with 2y plus 2, so we could pull the square root of 5 in front, so we get 2 pi square root of 5 in front, integral from 0 to 2 of 2y plus 2, that's with respect to y. Yeah, so then you just find an antiderivative. So antiderivative of 2y would be y squared. Squared derivative is 2y, right? And then antiderivative of 2 is 2y. And you can plug in 0 and 2. If you plug in 2, you get 4 plus 4, and you plug in 0, you get 0 plus 0, so that equals 8. But then we still have to multiply by the 2 pi and the square root of 5, right? So 8 times 2 pi times square root of 5 equals 16 pi square root of 5. And then that's your final exact simplified answer. Because it was a surface area, this is going to be in square units.